In this video, I wanted to go over the homework 7, which is kind of an exam review. And so for number 1, this is you just have a rate, and it says, what are the units of the rate constant for the following equation? And this should be pretty straightforward by now. First of all, you know that the units for a rate should be some amount, so like moles per, and then you could say liters second, so some amount per volume time. And so if you put that in for the rate, then you can plug in the units for the pressures that are in this particular equation, and you can figure out what the units for K are. So for instance, I'll just write this down. This is number 1. You have this rate minus RA is equal to K, PA to the 1/2, PB to the 1/2. So then you can write the units for the rate, so you know that that should be moles per, say, liter second. And then you can start writing units for other stuff. So you have K, and then you have pressure to the 1/2 and a pressure to the 1/2. So then these just combine, so then you just have pressure. So then you know that the units for K need to be mole per liter per atmosphere per second. So for number 2, it says the following reversible gas phase reaction takes place in a PBR. So this is 2. First of all, you know it's reversible. You know it's a PBR. The feed to the reactor is equimolar in A and B, so equimolar in A and B. It gives you alpha, and says develop the 2 ODEs in terms of conversion of A and Y, so the pressure drop, for this system with the appropriate boundary conditions. Forward reaction rate is K, and the equilibrium constant is, so you have K and K. The reaction is isothermal, so isothermal, and elementary in both directions. So all you need to do for this problem is formulate or write down the ODEs that you would need to solve. And so I don't think this is actually asking you to solve anything. So you would just approach this the exact same way as all the other problems. First of all, do a mole balance. So this is a mole balance for a PBR, so it's dx dw is equal to minus RA prime over FA naught. And remember that since we have a pressure drop, this needs to be written in the differential form. And then we have a rate law, and so just assuming that this reaction is A plus B to C plus D, then the rate law would be minus RA prime is equal to K CA CB minus CC CD minus CD over K. So if you're unsure about how, so I just wrote this down, I didn't want to spend time deriving this in this video, so if you're unsure about how this was derived, then make sure you review rate laws for reversible reactions. So then after you get the rate law, then you do the stoichiometry. And so we know that CA is equal to CA naught 1 minus X over 1 plus epsilon X Y, and we know this because it's gas phase, and we have a pressure drop. So CB is equal to CA naught 1 minus x over 1 plus epsilon x y. C of C is equal to Ca naught x over 1 plus epsilon x y. And C of D is equal to Ca naught x over 1 plus epsilon x y. So you should be able to just write this stuff down. At this point, you should be able to just go through this and not have, I mean, you have to think, but it should just come, like this should just be, you should just be able to go through this and write this down. And then for this one, we have a pressure drop, so pressure drop, and this is dy dw is equal to minus alpha over 2y 1 plus epsilon x. So then if I had a problem like this on the exam, I would go through and, so you don't need to solve this, but I would probably write these into the rate law. So then I have a rate law, and then I'd say, so for instance, plug that in there, that in there, that in there, and that in there. Like I would write that down. And then, so then I have the rate law, and it's all in terms of these. And then for the ODEs, you need to write down what you're solving them at. So for instance, for dx dw, when w is 0, x is 0. And for dy dw, when w is 0, y is 1. So just make sure, like if you get a problem like this where it asks you to just write down the equations you would put in your solver, make sure that you write down what your limits are and your initial conditions. And then also if you're given values for these things, like say alpha is 0.01, then make sure you write that down just so that it's really clear that we know what you're planning on plugging in. So that's all I'm really going to say about that problem. 3, it says, in the following reaction, so then it gives you this reaction, A plus B to C plus B. B is a liquid phase catalyst that is produced at the same rate as it is consumed. And then it gives you the rate, so minus RA is equal to K CA CB, and K is equal to 0.2 liters per mole per minute. And then it says the reaction takes place in a semi-batch, so you have a semi-batch in which 100 liters of a solution containing 2 moles per liter of A is initially present and no B. So you have V naught is equal to 100 liters with Ca naught is equal to 2 moles per liter, and Cb naught is equal to 0. So then it says to start the reaction 5 liters per minute, so V naught is equal to 5 liters per minute of a solution containing 0.5 mole per liter of B, so so Cb, so this is Cb naught in the reactor, and then this is Cb naught in the solution, I guess, so 0.5 moles per liter. And then it says formulate an ordinary differential equation that would let you solve the problem as the conversion of A with time. Substitute all the relevant values and specify the initial conditions. So I'm going to change that to just no B initially. So the first thing we want to do is a mole balance. And we want the mole balance for a batch reactor, and we want it to be in terms of conversion because it's asking to formulate the ODE that will solve for conversion as a function of time. So we know that that is NA naught dx dt is equal to minus RAV. And then the rate, and the rate was given, so it was minus RA is equal to K CA CB, and then the stoichiometry. And so we know that CA is equal to NA over V, and that is, and NA is equal to NA naught 1 minus X, and then V, we know that V, the volume is changing since this is a semi-batch, so this would just be V naught plus V naught T. So this is the initial volume plus the volumetric flow rate multiplied by time, so the amount that's added over time. And then CB is also equal to NB over V. But then since we're adding B to the reactor, this is slightly different. So we know that it's NBI, what's in there initially, plus FB naught T, what's added, minus NA naught X, what has converted, divided by V naught plus V naught T. And then we know that there's nothing in there initially, so that's 0. And then we also know that B isn't converted in the reaction, so it says, actually it says that the liquid phase catalyst is produced at the same rate as it is consumed. So this ends up being 0 just because it would also add because you're losing it, so you're losing a certain amount, but then you're adding the same amount, so so you would actually have a plus NA naught X, and so that would just cancel out. So then if we rewrite FB naught as CB naught V naught, this becomes CB is equal to CB naught V naught T over V naught plus V naught T. So then you can just combine everything. I'm going to erase this real quick. So if we combine this into here and that into there, we get, oh, this is NA naught, not NA. So we get NA naught dx dt is equal to K NA naught 1 minus X over V naught plus V naught T CB naught V naught T over V naught plus V naught T. And then remember this volume is changing, so we can't just write V here. We have to write V naught plus V naught T. So then one of these cancels, and we can also cancel NA naught. And so we're left with dx dt is equal to K 1 minus X CB naught V naught T over V naught plus V naught T. So this is the equation, and it doesn't say that you need to solve it. It just says formulate the ODE that would let you solve the problem as a conversion of A with time. So we've done that because this is the conversion of A. with time, and then it says substitute all the relevant values and specify the initial conditions. So putting in the relevant, well, first of all, the initial conditions, we know that at t equals 0, x is equal to 0. And then as far as the initial values, CB naught was given as 0.5, V naught was given as 5. The initial volume was 100, and K was 0.2. So then you could just plug these into this equation, and that should be it. For number 4, it says you have a first order reaction, so first order with rate constant of 0.2939, so K is equal to 0.2939. It's taking place in a recycle reactor, so you have a recycle reactor where 80% of the immediate exit stream, so here's your reactor, and then this is coming back. So 80% of the immediate exit stream, so the immediate exit stream is right here, so that would be FA2. So 80% of that is recycled. So 80% of FA2 is recycled. The initial concentration in the fresh feed is 2 moles per liter, so CA naught equals 0.2 moles per liter. The volumetric flow rate is 10 liters per second, so V naught is 10 liters per second, and the reactor volume is 100 liters, so volume 100 liters. There's no volume change in the reaction, so V equals V naught. And it wants to know the final exit conversion, so that's out here. So it wants to know X naught. Because if you remember with recycle reactors, you can have the conversion here. So this is what I've been calling XS, so like S for a single pass, and then X naught, or I think this is also being called XF, so X final or X naught. But anyway, this is what you're looking for. So if this problem showed up on the exam, this is what I was talking about in the previous video on the exam review, that you probably don't want to go through and derive the equation for the recycle, or you don't want to derive the integrated equation for the recycle reactor, you just want to write it down. So for instance, in this case it says it's first order, so we know the first order integrated equation is tau K over R plus 1 is equal to the natural log CA naught plus R CAF over R plus 1 CAF. And if you remember that, so I'm just going to write down the equations that you would use to derive this real quick, just so you know, but just so you know, like if you see first order or second order recycle reactor on the exam, you probably want to skip directly to the integrated equation, but unless it specifically tells you to derive this or to set up and integrate the equation. So the way you would come up with this is, first of all, you would do a mole balance. So this is the mole balances that I'm using is V is FA naught 1 plus R R over R plus 1 x naught dxa over minus R a. And so if you remember, there were actually two equations you could use, and I'm using this one because the math ends up being easier, but just don't get confused about that. And then so you have a rate law, and it says it's first order, so minus RA is equal to K CA, and then the stoichiometry CA is equal to CA naught 1 minus XA. And so then what you would do is combine this into here, this into here. You would integrate this, and then after you integrate this, you end up with an equation that's in terms of x naught. And so to get this in terms of this equation, you would use this relation where x naught is equal to CA naught minus CAF over CA naught. So then you can switch back and forth between those variables, and not, or this is x naught or x final. I mean, sorry, I'm kind of switching what I'm calling the variables, but both x naught and xf are the same thing. They're the conversion out of the, so it takes into account the conversion for the entire system. I'm going to erase this stuff and just write down real quick the equation you would get in terms of x naught, either if you solve this or if you solve this for CAF and plug it into here. Although to solve this, to get XF, we don't actually need to do that. We can work with the equation in this form. So I'm just going to erase some stuff real quick. If we rewrite this equation in terms of x naught, we get tau k over r plus 1 is equal to natural log r x naught minus 1 over r plus 1 x naught minus 1. But it turns out you don't actually need the equation in this form to solve it, because using this relation, so using the, okay, so we know that x final is equal to CA naught minus CAF over CA naught. We can figure out what CAF is from this equation. So what you would do is plug in your value for tau, which you know is 10. So tau is equal to V over V naught. You know K. We can figure out what R is. We know CA naught. So you can plug everything into here and calculate CAF, and then you can solve this equation for x final. So the way you figure out R is, you know that R is equal to FAR, so that's the stream, over FA3, and that's the stream out here. So FAR plus FA3 is equal to FA2. And we know that 80% is recycled, so we know that 80% of the stream comes this way, so we know that this is 80, and so if 80% is going this way, then 20% has to be going this way, so then we know this is just 4. So if you plug R into here, tau, K, and solve for CAF, you get that CAF is equal to 0.4, and then you can plug that into here, and we know CA naught. I wrote down CA naught wrong. This is 2 moles per liter. So anyway, so for this one you can just plug in CA naught, so 2 minus 0.4 divided by 2, and you end up with 0.8, so 80% conversion. And you could also solve this from here. You could just plug in, like say you had this equation, you can plug in tau, k, r, and just solve this for xf. And so if you do that from this equation, you'll also get the xf is equal to 0.8. For number 5, it says you have a first order gas phase reaction, so first order gas phase, and it's A to B. It's in an isothermal packed bed reactor, so PBr isothermal. The temperature of the reaction is 127, so T naught is 127 degrees C, and P naught is 5 atmospheres. The volumetric flow rate is 5 liters per minute, so V naught equals 5 liters per minute. The pressure drop parameter alpha is 0.005 kilograms minus 1. The reaction rate is given by minus Ra equals K Ca, and it gives K is equal to 0.05 liters per kilogram catalyst per minute. The reactor is packed with 100 kilograms of catalyst, so W is equal to 100 kilograms. And it says determine the conversion in the reactor, so we want to find X. So the first thing you want to do is start with the mole balance. And that is dx dw is equal to minus Ra prime over Fa naught. And so first of all, we need to use the differential form of the equation because there's a pressure drop. And second, I'm selecting the equation in terms of conversion because that's what we're looking for. So that's why I'm using the dx dw instead of like in terms of concentration or something like that. And then the rate was already given, so we know that that's minus Ra is equal to K Ca. Stoichiometry, it's gas phase, so we know that Ca is equal to Ca naught 1 minus x over 1 plus epsilon x y. And y is for the pressure drop. And then we need to write an equation for the pressure drop, and that is dy dw is equal to minus alpha over 2y 1 plus epsilon x. And so just looking at these equations, we have two coupled ODEs, but it's asking us to solve this for x. So if we want to get an analytical solution for this, we need to solve this equation first for y and plug it into here. And the way, if you remember, the way you can do that is you can assume that epsilon x is approximately 0. And so this is what you need to do for this problem. And so if you make this assumption, just make sure that you specify that you're assuming that. So with this assumption, then y is equal to 1 minus alpha w to the 1/2. And I'm just going to erase some stuff real quick. Let me just combine everything and solve this. So we are plugging this into here, and that into there. So if we do that, we get that dx dw is equal to K Ca naught over Fa naught. This is 1 minus x over 1 plus epsilon x, 1 minus alpha w to the 1/2. And I'm also assuming that's approximately 0, so I'm just going to take that out of the equation. You could leave it in there to stay more general, or you can take it out. And so if we separate and integrate this, we get 0 to x dx over 1 minus x is equal to k, and then we know that this is equal to CA naught V naught, so we can cancel out the CA naught. So if we do that, we get k over V naught, 0 to w, 1 minus alpha w to the 1/2. So then solving this, we get minus ln 1 minus x is equal to k over V naught 2/3 alpha 1 minus alpha w to the 3/2. So then we should have everything we need to solve for x. So we know what k is because it was given. We know alpha, we know w, and we know V naught. And so solving for x, you get that x is equal to 0.58. Number 6, it says the following rate versus conversion data was obtained. So you have a concentration and a rate, and he gave you data for those, and then it says determine the order of reaction and the rate constant. So for the concentration, you have 0.2, 0.1, 0.04, 0.025, 0.02, and for the rate you have 0.02, 0.005, 0.0008, 0.0003, 0.0002. And then we can write down the equation for the rate. So the generic rate equation is minus RA is equal to K CA alpha. And so it's asking us to determine what alpha is and what K is. So for this problem, it's a little bit different from some of the other data problems we were given because you have a concentration and a rate, whereas before you were given a concentration per time. And so just don't overthink this problem. If you look at this, we can say something like, okay, basically we can take a ratio of this because we know that alpha will be the same for both. So we can say RA1 is equal to KA CA1 alpha over RA2 is equal to KA CA2 alpha. And so then if we put in, so we know what the concentration is for this first rate, and we know what the concentration is for the second rate, the KA's cancel. And so if we just plug in some numbers, so for instance rate 1 is 0.02 is equal to, and the concentration is 0.2 alpha over, and then the second rate is 0.005 is equal to 0.1 alpha, then we can solve this for alpha and we get 2. And then we can find Ka. So we know that, say, going back to rate 1, we know that Ra1 is equal to Ka Ca1 squared. And we know that K is the same for all of them, so just plugging in some numbers. So 0.02 is equal to Ka, and then Ca1 is 0.2 squared. So then if we solve that for Ka, we get 0.5. For number 7, it says you have a liquid phase reaction, so liquid phase, and that it's A plus 2B to C. It's a semi-batch reactor. Says the reaction began with 84 moles of A in the reactor, so Na equals 84. The initial reactor volume is 50 liters, so V naught is 50 liters. And this is moles. The reaction is assumed to be zero order with respect to A and B, so we know that minus Ra is just equal to K. The rate constant K is 0.125. How much time does it take to reach a conversion of 50% of A? So XA equals 0.5, and we're looking for the time. What is the concentration of B at this time? And so then CB at T. B is at a volumetric flow rate of 2 liters per minute with an initial concentration of 10 moles per liter. First thing we want to do is a mole balance for batch reactor. And we know that we're looking for conversion, so we want to write our mole balance in terms of conversion. So Na naught dx dt is equal to minus RAV. And we know the rate law is just K. Stoichiometry, we have that Ca is equal to Na over V, and Na is Na naught 1 minus X, and then V, remember the volume is changing, so this is the initial volume plus whatever's added. And then for Cb, we have Nb, and you don't even really, well, actually we do need an equation for Cb. So Cb is equal to Nb over V, and that is equal to what we have initially plus what we add minus what was reacted. And looking at stoichiometry, we know that for every one of A reacted, 2 of B are reacted. So this is 2 Na naught X over, and then remember the volume's changing. So then we can, really to integrate this, we just need to plug that into there and we can integrate. So I'm just going to erase some stuff real quick. Combining this, so combining the rate law into the mole balance, we have Na naught dx dt is equal to K, and then this is multiplied by V, and if you remember, V is V naught plus V naught T. So then we can separate and integrate, and if we do that, we get 0 to T V naught plus V naught T dt is equal to Na naught over K 0 to X dx. So then integrating this, we get, this one is T squared V naught over 2 plus V naught T is equal to Na naught K multiplied by X. The question was, when X is equal to 0.5, what is T? So we should have everything we need. We know what Na naught is, we know what K is, we know what V naught and the volumetric flow rate are, and we know X. So if we plug all that in, we get that T is equal to 6 minutes. And then the second part of the problem, it asked for the concentration of B when at that time. And so if we go back to this equation, first of all, we know that this is 0 because initially there wasn't any B in the reactor. We know that this is C B naught V naught. So we end up with an equation that looks like CB equal to CB naught V naught T minus 2 NA naught X over V naught plus V naught T. So we should have everything we need. We know what CB naught is, we know what the volumetric flow rate is, we know what the time is, we know what NA naught is, we know what X is, and we know what the initial volume and volumetric flow rate are. So if we plug all that in, we get that this is equal to 0.58 moles per liter. So number 8 says you have a series reaction, so you have A to B to C. And this is first order, and this one's 0 order. It's in a CSTR, so CSTR, and it says derive the concentrations of A and B as a function of residence time tau. The rate constants of, so you have K1, K2, you have CA naught. Assume that the concentrations of B and C in the reactor entrance stream are 0, so CB naught equals 0, CC naught equals 0. So really we just need to derive the concentrations of A and B as a function of residence time tau. So the first thing you want to do when you have a series reaction like this is so we want to split this into 2 reactions and number them. So the first one would be A to B, and the second one would be B to C. And then we know the first one is, this one is first order, so we know that minus RA, and this is R1A, is equal to KCA, and then this one's 0 order, so this would be R2B is equal to K. So now we want to do a mole balance. So we know if we look at we get the mole balance, this is from chapter 1. V is equal to FA naught minus FA over minus RA. And then we can rewrite this as CA naught V naught. So this is equal to CA naught V naught minus CA V naught over minus RA. And then we can divide, because it said that it wanted it in terms of resonance time. And so we know that that's V over B naught. So if we divide over the B naught, we get tau is equal to CA naught minus CA over minus RA. And then we can write the same thing for B. So we have tau is equal to CB naught minus CB over minus RB. And we can also write this for C of C. So tau is equal to C of C over RC. So I'm going to erase some stuff and then go over the rate law for this. For the rate law, we know that, so we have we need to write the net rate law, if you remember, for multiple reactions. And so first of all, we know that minus, well, I'm just going to write RA is equal to R1A. So this is R1A 1A. And we could also, just for completeness, write plus R2A, so A in reaction 2, but we know that there's no A in the second reaction, so that would just be 0. So then we can do the same thing for RB, is R1B plus R2B, and in this case we have B in both of them, so this is like that. And then RC, and we can do the same thing, R1C plus R2C. There's no C in the first reaction, so that's 0. We need to figure out what, so we know R1A and we know R2B, so we need to figure out what R1B and R2C is. So we can do that with stoichiometry. So we know, so starting with reaction 1, we know that R1A over minus 1 is equal to R1B over 1. So then we know that R1B is equal to minus 1 multiplied by R1A. So this is just equal to K1CA. I need to label these K1 and K2. So then for reaction 2, we know that R2B over minus 1 is equal to R2C over 1. And so then we know that R2C is equal to minus 1 multiplied by R2B, and so that is equal to K2. You can combine these to get your total rate laws, so doing that we know that, so I'm just going to write combine. We know that RA is equal to minus, so we already knew what R1A was, that was just minus K1CA. RB is equal to, and then we know that R1B is equal to this, so minus 1 multiplied by R1A, so it was K1CA minus, and then R2B, so we knew what that was K, and RC is equal to R2C, which was K2. And then at this point you can kind of double check your signs. So just writing down the reactions again, we had A to B and B to C. So for the first one, it's the rate of disappearance of A, but it's written as rate of appearance, so this should be negative. So that's right. And for RB, we have the rate of appearance of B, and so in the first one, B is appearing, but in the second one it's disappearing, so we should have plus minus. And then for the third one, this is appearing, so this should be positive. Do is just plug these. So I'm going to erase some stuff and write down the mole balances again real quick. So for the mole balances, we had tau is equal to Ca naught minus Ca over minus Ra, and tau is equal to Cb naught minus Cb over minus Rb. So what we can do at this point is just plug the rates in. So for this first one we have Ca naught minus Ca over, and then the first rate was minus K1Ca, so minus K1 Ca, and then for the second one we have Cb naught minus Cb, and then this rate was K1 Ca minus K2. So then we can take this first equation and, I mean, technically this is the answer, but I want to put it in terms of Ca over Ca naught. So I'm going to divide through Ca. So if you do that, you get tau is equal to Ca over Ca naught over Ca minus 1 over Ca, whoops, K1. So I just pulled the Ca out of here, and then that cancels, and then I can rewrite this as, if I solve this for, I want to solve this for Ca over Ca naught, and if I do that, I get that Ca over Ca naught is equal to 1 over 1 plus K1 tau. You can do a similar thing for Cb, and I'm not going to go through all the details of the math, but for Cb, you should end up with something that looks something like Cb over tau is equal to K1 Ca naught over 1 plus K1 tau minus K2. For number 9, it says determine the composite rates of reaction for all of the species in the following reaction sequence. So for number 9, it gives you the following reaction sequence. So you have A, and then this one is K1 first order, K2 first order, and this is B to C, this is K3 first order, and then you have 2A to D, and this is K4, and this one's also first order. Wait, sorry, this one's second order. So all this is asking for is your net rate laws, so RA, RB, RC, and RD. And so what you want to do is, and this is what you want to do with any problem that you have in series, or if it just gives you a series of, or a list of reactions that are occurring together, you always want to number them. So I'm going to renumber this as A to B, and then just writing the rate law for R1A. This is a reversible reaction, so this would be K1 Ca minus Cb over K. And remember, this is different from, these two K's are different. And this is the equilibrium conversion. So, and I don't want to go through the details of deriving this because I've already done that in a different video. So this is just the rate law for a reversible reaction. So if you're confused about how this was derived, then make sure you go back and review that. So for the second reaction, I have B to C, and then it says this one's first order, so minus R2B is equal to K3 CB. And then the third one is just 2A to D, and so minus R3A is equal to K4 CD squared, actually Ca squared. So this is when you're doing these problems, the most important thing is to just keep all your numbering straight. So I numbered these 1 to 3, and then this rate law, this is R1, this is RA in the first reaction, so it's R1A. This is B in the second reaction, so it's R2B. And then this is A in the third reaction, so this is R3A. So this first number is just the reaction number, and then the second one is whatever your species is. And so just make sure you keep that really clear. Otherwise, these problems can get kind of confusing. So then we want to do the net rates. So for the first one, RA, and I could do the same thing I did before where I just say R1A plus R2A plus R3A. And then I know that R2A is 0, so this is just R1A plus R3A because I have A in 1 and 3. And then same thing for RB. I have B in 1 and B in the second one, so R2B, RC, and I only have C in the second one, so R2C, and RD, I only have D in the third one, so this is R3D. So I'm going to erase some things real quick. Next thing you need to do is figure out, because we know what these are now, and we know R1A, we know R1B, wait no, we know R2B, and we know R3A, but we don't know we don't know R1B, we don't know R2C, and we don't know R3D, so we need to figure out what those are. So relative rates, and so for reaction 1, we have R1A over minus 1 is equal to R1B over 1. So then R1B is equal to minus 1 multiplied by R1A. For reaction 2, you had R2B over minus 1 is equal to R2C over 1. So then R2C is equal to minus 1 multiplied by R2B. And then for reaction 3, you have R3A over minus 2 is equal to R3D over 1. So then R3D is equal to minus 1/2, because we just multiply the 1 over, R3A. So combine. So for the first one we have RA. Well, I'm just going to write down what they were real quick again. So for the first one we had RA is equal to R1A plus R3A. RB was equal to R1B plus R2B. RC was equal to R2C. And RD was equal to R3D. So then just plugging in these equations that we just derived. So first of all, we know that R1A was minus K1 CA minus CB over K. And then we have minus R, so minus R3A, and that was K4 CA squared. So then if you remember, this is written as the rate of appearance. So if we wrote this as the rate of disappearance, then this would be minus RA is equal to K1 CA minus CB over K plus K4 CA squared. So then for RB, we have R1B, which we knew, no, we didn't know. So this is R1B, so this is minus 1 multiplied by R1A, so you end up with K1 CA minus CB over K plus R2B, and that was so R2B, so this would be minus K3CB. And this makes sense the way it's written, because we know that this is the rate of appearance, and we know that it's appearing in reaction 1 and disappearing in reaction 2. So for RC, we have R2C, which was minus 1 R2B. So R2B was K3CB, so this should be K3CB. And then for RD, that's R3D, so we have minus 1/2 multiplied by R3A, which was K4CA squared. So these are your composite rates of reaction.